Good evening, everyone, particularly those of you who are present here in person, and also those of you who have joined us via remote Teams. Just a quick reminder, this is the second of the 4 sessions planned for the Royal Aeronautical Society teachings. And today, we will be looking at the use of FlameMaker for creating the models. Now, aircraft design is a fairly involved and a complex subject, and I cannot profess to impart all the knowledge which is out there in 2 or 3 sessions. The principal objective of these sessions remain to enthuse budding aspiring aircraft designers to use software tools to facilitate the design process. Now, just to recap and recall, the aircraft design process is quite involved, generally starting with some form of a conceptual review, where we're trying to tie down some fundamental top-level aircraft requirements, followed by a preliminary design review, which looks at the sizing and the functionality in a little bit more detail, evaluate to not a great deal, but to some extent, the stability aspects of the aircraft that is under consideration. And of course, once the aircraft goes through the preliminary design stage, we can then start to cross the T's and dot the I's in terms of the details. So once the detailed design review is complete, we can then proceed to produce a prototype. Now, where does one start? Now, that's often the most difficult question. Where do you start in terms of choosing the aircraft design parameters? In the last session, I put up a couple of tables and also a couple of graphs. These graphs are essentially for the tail sitters and nose wheel aircraft less than 2 tons, i.e. light aircraft. And if you look at the first table, which is that one, that's all to do with the nose wheel aircraft. And if I plot the power loading versus the wing loading, I get a fairly flattish response shown on the right. So assuming a particular wing loading, I can start off with a fairly good guesstimate of my power requirements for the aircraft. 80 kilograms per square meter is a fairly decent wing loading for a light aircraft. So if you assume that to be the case, then corresponding value will be roughly about 120 watt per kilogram as far as the power requirement. So it size the engine more or less. Similarly, for the tail sitters, we have a similar relationship, which is on the right-hand side. Sorry, left-hand side, sorry, I'm getting my left and right confused. So there, and again, here we presented the thrust to weight ratio. So a thrust to weight ratio of around 0.5, 0.4 will be quite acceptable as a starting value. Now, don't forget that the aircraft design process is iterative. So you are not going to get the answers on the first attempt. It will have to be iterated upon many times until multiple constraints and multiple requirements are satisfied. So the purpose of today's session is to go through a very simple design that we will be able to recreate in today's session and hopefully plug. Just to sort of stress, I have not spent a great deal of time designing this particular aircraft that I'm going to be talking about. Okay, I really spent 2 hours. And then I got Matthias, who's sitting in the room whilst I was driving back home last night, to actually put the data in FlameMaker. And today I was able to modify a few things, fine tune it. So we've got a flying aircraft. So the first thing we need to decide is the layout. So the simplest layout generally tends to be the conventional layout. So for today's session, I've chosen a conventional layout without any dihedral, without any complexity, without any complex empennage arrangement, a simple conventional aircraft we're going to design. Okay. Now at this stage, the important things are how many engines you're going to use, what kind of undercarriage arrangement you're going to use, and what your target maximum takeoff weight needs to be. That's quite important. If you get that right, you will tend to get most things right. So for the power loading that I have chosen, for the wing loading I have chosen, around 850 kilograms would be a good starting point for my maximum takeoff weight. So where do we start? The first thing is I need to determine what my wing loading is. So based on competitor analysis, I chose a wing loading of 85 kilograms per meter squared, not cube, squared. We change the. So there's a typo there, it's not a cube, it's a square. And we're going to choose a thrust to weight ratio of around 0.5. So what comes next? A 120 watt per kilogram power pack will do the trick based on competitor analysis. Important choice at this stage would be an aspect ratio. Now, aspect ratio, the choice is quite crucial. Why? Because if you choose too big an aspect ratio, then yes, you can reduce the drag, but you have structural implications. If you choose too low an aspect ratio, the wing loading becomes quite prohibitive. So you need fairly strong materials. So for a small aircraft, anything between 6 and 7.5 would be a reasonable choice as a starting point. So I've chosen 6. What shall be my stall speed? I've chosen a fairly low stall speed that gives me something around 20 odd knots. Pretty slow. I then need to determine what my CL max need to be. That's simple. If I've chosen my stall speed using the lift equation, organize so using that equation, I have chosen my wing loading, I have chosen my stall speed, I can work out the maximum CL. So for this particular arrangement, I'm looking at a CL of around 0.96. What airfoil do I need to choose? Obviously, if I choose a complex airfoil, then manufacturing becomes an issue. So I want to choose a relatively simple airfoil that can give me the CL max at the stalling angle. So if I look at the airfoil tools, it transpires that the NACA 24 series, 2% camber, thickness at 40% maximum, with 10% thickness overall, gives me a CL max of around 1 or just over 1. So that would be a reasonable choice. At this stage, the only thing I need to mention is that when you go to airfoil tools, the data that you get is 2D. So you have to account for the 3D effects. So we can make the correction in terms of the lift curve slope of the airfoil by a suitable correction, in which case we may have to go back and choose an airfoil that gives us a slightly higher CL, so that by the time we account for the correction, we get the maximum CL that is going to satisfy our stall condition. As I said, I designed this aircraft in 2 hours yesterday. Okay, so it might not look the world's most prettiest aircraft, but it certainly will fly. And then, of course, we can spend a lot of time tinkering with it to make it look pretty and make it do things that we wish. By the way, these notes will be available at the end of the session, so you don't have to make any notes. We started off by choosing a takeoff weight of 850 kilograms. So what are the sort of things that we need to decide on for an aerodynamic surface? Obviously, the wing area is important because that is going to generate the lift for us. We need the taper ratio, we need the diagonal, we need the wing setting angle, we need the root chord, the tilt chord, and if you have a taper, then of course we need aerodynamic chords, etc. So those are the typical parameters that you would need from an aerodynamic surface. So how do I make it simple? I take a planform wing, taper ratio of 1, I have the same root chord, tip chord, I've chosen my aspect ratio, I've chosen my wing loading, I've chosen my maximum takeoff weight, I have the wing area, I have the aspect ratio, I can then determine my span. The aspect ratio is b squared over s. So it's very simple. So once I have those numbers, I'm not going to put any quarter chord sweep because it's a planform wing. I'm not going to do any washout. Generally speaking, if you put a washout in, then your tip is going to stall a little later than your main wing. So you'll have control effectiveness, but we are assuming to be a fairly plain standard wing. You also see there are a few limitations in X-plane. For example, when we're designing the wing will get split up into multiple sections. And then, based on how many sections you divide the wing into, your control surfaces will be a fraction of those segments. So you can have either 2 segments worth, which could be 20%, or 3 segments worth, which would be 30% of the semi-span of the wing. So we want to keep it simple. If we do the competitor analysis at this stage for similar sized aircraft, we will find that the fuselage length would be anything between 6 meters to about 8.2 meters in the same maximum takeoff weight. So we've chosen 6.5. Now there are means of computing that as well. So if you refer to RAeS' book on aircraft design, there are some empirical relationships that allow you to determine the fuselage length even at this stage. So I'm taking a pot guess at 6.5 meters. And as I said before, what we want for the empennage to have good control power that allows to maneuver the aircraft in pitch. Now for that, generally speaking, we would choose the aspect ratio to be lower than the main wing, but how much lower? If you look at this graph, what transpires is reducing aspect ratio reduces the slope of the curve, which means that for large alpha, you produce small CL, which means lift. So increasing the aspect ratio of the tail of the empennage, the horizontal tail particularly, will mean that your control effectiveness is improved. However, there is a cost for that. High aspect ratio wings have structural implications. So my choice, anything between 4 and 5 does the trick at this stage. So I've chosen 4. Now comes the next important bits. We need to choose the sizes for our empennage, especially the horizontal tail. We need to size our fin. We need to size our control surfaces. So what we're going to use at this stage is to assume that we're going to produce a CG margin of around 10%. So knowing where my central pressure is, where my wing is located, I can determine where my CG needs to be. So that's an important choice at this stage. The horizontal tail area, as an initial guess, needs to be anything between 25 to 30% of the main wing area. And that generally gives us fairly good results. The tail volume coefficient for small aircraft, particularly around the sort of 800 to 2,000 kilogram mark, anything between 0.55 to 0.65 as the tail volume coefficient for the horizontal tail. Now, using the formula indicated, which is the area of the horizontal tail multiplied by the tail arm divided by the wing area times the wheel dynamic chord, with V bar assumed to be 0.55, with the wing area computed before, the tail or horizontal tail area computed as 30% or 25% of the wing area, I can work out the tail arm. That means if I position my wing, I can position my tail a suitable distance away. And this is the tail arm, in my case, 3.54 meters away. Just again, a very quick reminder that the center of pressure would be around the quarter chord. Okay, so this distance, the tail arm, is quarter chord to quarter chord. So quarter chord of the main wing to the quarter chord of the horizontal tail. The vertical fin, tail volume coefficient, is also an important entity. You want to be able to control the aircraft directionally. So generally speaking, again, a rule of thumb, if you scour the various textbooks on aircraft design, they will tell you that for light aircraft, the vertical tail volume coefficient needs to be anything between 0.03 to 0.05. So with that as a number, I am able to determine the tail arm for my vertical fin. Now, if I co-locate the center of pressure of the vertical fin and the horizontal stabilizer, you notice that both those numbers come out the same. One comes out at 3.54, the other comes out at 3.5. So they're co-located, the center pressures are located on top of each other. Now comes the choice for the control surfaces. As I said, there is a slight limitation in X-plane as much as that we can't divide the wing section or the aerodynamic sections in 100 pieces or 100 segments, giving you a much finer resolution in terms of the control surface sizes. Now, from a design point of view, what we've said is the ailerons need to be roughly 5% to 8% of the wing area. Okay? And the chord needs to be 20% of the mean aerodynamic chord. So if you have an aileron about that size, it'll give you enough roll authority. The elevators need to be between 15 to 20% of the area of the horizontal stabilizer. And again, the chord could be as little as 20, depending on the tail arm. If it's short coupled, you need a bigger chord. If it's tail arm is sufficient, then you get away with a smaller number. Otherwise, you end up with 40% short coupled. Rudder area, 15 to 30% of the fin size. So once you determine the fin area, SV, then 30% of that would be the size of the rudder. The chord of the rudder would be between 20 to 30%. So with all of that, we actually have a basic geometry. We can now use Plane Maker to actually construct an aircraft. So the idea today was to use as much time as possible playing with X-Plane, and I just wanted a quick half an hour, let's say, intro into the fundamentals of aircraft design, and I think I've been quite successful in doing so. The last slide, not the least, is directly from the horse's mouth. Austin Meyer, who was the developer of X-Plane, there are two videos. One which is the use of the airfoil maker. So there is the manual. The first link is to the manual from the X-Plane. So for the online audience, so this is the link to the online resource, which is the airfoil maker, and Austin Meyer's airfoil maker video, which is the second link. It's a must-watch. If you want to design airfoils, it's an absolutely must-watch because he explains the very detailed workings of airfoil maker. Similarly, there's two other resources that I would like to point out. One of them is the Plane Maker manual, which is the first link here. And the second link is Austin Meyer's Plane Maker video. And he actually goes through in very elaborate details as to how to construct the models. So what we're now going to do is we take a quick 5-minute breather, by which time I hope the online audience will be able to fire up their Plane Maker. Okay, so would you all like to fire up your Plane Makers? Okay, so I assume that everybody's got Plane Maker up and running. So the first thing I'm going to do is explain to you the menu system of the Plane Maker. So the first and foremost is the about, which basically tells you what it is. It's a fairly standard thing. The next menu system is the file menu system, and that allows you to open an existing aeroplane or design a new one. So what we're going to do is I'm going to, in my case, open an existing aircraft that I designed, but then I will take you through all the steps. Okay? So in my case, I want to open up an existing design. In your case, you will all open a new design. So you'll all open the new design, whereas I will open an existing design. So let's open. There you go, finally. It doesn't look very pretty, but it's an aeroplane. So what we need to do is to start, we look at the standard menu items, and when you click the menu standard, you will see the author. So the first thing we need to do is we need to type in the basic things about the aircraft that you're going to have. Things like the name for the plane, the call sign. Most importantly, you will see right at the bottom of that screen what type of an aircraft that is. The reason is that when the aircraft is built, it will come up in the X-Plane's directory structure when we select an aircraft in one of those categories. So it could be an experimental category, or it could be a seaplane, it could be VTOL, it could be an airline, or whatever. So here we're going to select experimental. Okay. So once we're happy, that will basically be how that plane is now going to be referred to. Okay. So the next thing that we need to do is, if everybody is happy with that, yeah. Click standard again, and the next menu down the list is viewpoint. What the viewpoint does is allows you to set the viewpoint of the aircraft in question. There are keyboard shortcuts. So for example, the W key rotates the aircraft, so you can see that. Then you can have other keys doing the same thing as well. So you just need to find out what the keyboard mapping is for rotating the aircraft view. Other menu items, 2D panel. So what we're able to do is we're able to create a panel easily by clicking the 2D panel. And then on the left-hand side of the menu system, you will see lots and lots of instruments. So whatever instruments that you need, I would suggest that we need the airspeed indicator, we need an artificial horizon, we need an altimeter, and we need an RPM indicator. So those 4 instruments for now would be sufficient. So to get an instrument, we can look at the standard 6. So further down that list, you will see an item called standard 6. So when I click the standard 6, it opens up into further options. The airspeed indicator, altimeters, artificial horizons, etc. So let's say we want to put an airspeed indicator on the panel. Then I click the airspeed. Then many other options are given to you. For example, you can have an angle of attack Q. You can have an angle of attack linear. You can have all sorts. So let's say to place any instrument, you first of all click it once, click it again, grab it, and put it in the cockpit anywhere you want. Okay, so as simple as. So you click it first, one click, the second click, grab and place the instrument in the cockpit. So now at this stage, you'll see X-Plane comes with every conceivable instrument that you can possibly use. Okay, so 4 instruments we want. The first is the airspeed indicator. The second would be the artificial horizon. The third would be the altimeter. And the final one would be the RPM gauge. Now to delete an instrument, it's very simple. You click and press the scissor icon on the top. So to delete an instrument, just click the instrument. So when it is highlighted, I use the scissor icon to cut it out of my panel. What you'll also see at this stage is on the right-hand side, the instruments that you have added. The properties of instruments are displayed on the bottom. So whenever I click an instrument, the properties will be displayed on the bottom here on the left-hand side. So for example, if it's an electrical instrument, then you can connect that electrical instrument to either electrical bus 1 or electrical bus 2, so that when we are doing a detailed system, shall we say, then everything is correct. So for now, we're not going to place too much attention to the electrical connectivity of the buses and instruments, okay? Because we want to get things running quickly. So if everybody is happy in getting some instruments on the panel, sorry? Okay, so you go to the engine. So to get the engine RPM, you will need to go to the engine, and then the engine has lots of dials and gauges, and you want the round gauges, so you can look at the engine round, and then that opens up a whole load of instruments that you can add. So it's a fairly straightforward thing to create your own cockpit layout. And the fact that you've got the instruments on your cockpit, X-Plane automatically knows that it needs to refresh them or update them when the simulation starts. Is everybody okay? Is everyone able to get the instruments on the cockpit? Yes? Do you have any feedback from the online users? Are they?
Yeah, they're responding.
They're responding positive.
So you can go to your headset.
Now you will have to play around with this segment in your own time, because there is a tremendous array of instruments available that you could use. So depending on what you really want to do, the choice of instruments, the layout would be dependent on that. But here again, we are only trying to get you up and running quickly, so we don't want a complex cockpit arrangement. Just get a few simple instruments so that when you start to fly the aircraft, at least you've got something to look at. Okay? And generally speaking, if you have the airspeed indicator, the artificial horizon, and if you have the altimeter, you should be able to fly the aircraft. Okay. And even if you don't have the engine RPM, you can hear the sound, and if it's making a whine sound, it's being revved up. So it's not an essential thing for you to have the engine RPM every day. But if you have, then it's fine. Okay, so can we move on?
Yes.
Okay, great, brilliant. So once we are happy, we click the left arrow key at the top, and that takes you back onto the main screen. So what shall we design first? Well, I know I'm going to use the 2410 for the main wing, and generally speaking, for the empennage, it's going to be a symmetrical aerofoil of some sort. So let's start off by assigning an aerofoil. To do that, we go to the expert section, and we click airfoils. Now I'm going to use a 2410, which sadly none of you are going to have. Okay, so you'll have to make do with what X-plane has. So the first thing is, it is going to be a propeller aircraft, so the first tab is the props. By clicking on the little button on the left-hand side, it opens up a menu item.
I think you need to.
Sorry?
No.
Not able to.
Ah, okay. In which case, we will leave that for a second. Let's go to start off with the fuselage. So let's do the fuselage first. To do the fuselage, you'll see 4 panes. The first pane defines how many segments I need to split the fuselage up. So 14 segments is what I've chosen. You can choose more if you want a better resolution. We can define the body radius. So how big is my cabin? And once I've selected the number of sections, what you'll see is you'll be given an ability to create a cross-section. If you want better resolution, then the number of radii per side needs to be increased. I'm just using 5 points to define my curve. You can choose a higher value. So if you are going to follow me, then you need to be looking at the same numbers. So if you type in the same numbers there, then we will get more or less the design that we're after. So number of segments or number of stations 14, and number of radii 5. Body radius of 3, that's feet, not meters. Leaving the area rule ratio to be fixed at 1. And we enter a drag coefficient based on the frontal area, 0.075. That's what I deem it to be. So with the number of stations created, you can look at these points, and by moving the mouse, these points can be moved arbitrarily wherever you want to create a shape. So if the shape is from the nose to the tail, you'll have the radii increasing up to the cockpit area and then decreasing towards the end of the fuselage, then that's what you're trying to do. You're trying to use the symmetry of the fuselage, and then you're looking at the cross sections, the 14 cross sections that you've chosen to give you the basic shape. So once those cross sections are defined, there's another thing we can do quickly, and that is we can look at the top and bottom views of the aircraft. You see what happened when I moved this first segment, I have created that. But even in that view, I can choose to drag these points and give it a shape. Alternatively, I can go back and change this to be what it needs to be.
Be defined by numbers directly. Coordinates.
Are you able to manipulate those points? Yeah, please. Okay. Sorry?
Use the others.
Can that be directly defined by coordinates?
We can do this manually, or you can use the tool at the bottom of the screen, which is the ellipse tool. To shape it in one place. So for people who are online, I'm asking the ACF file to be put in the chat so that you will be able to use that ACF file and follow me hopefully a little bit better. So another thing to note at this point is when we split up the fuselage in sections, the first parameter on the top is the distance from the datum. So where that section occurs, a certain distance away from the datum, and to change the distance from the datum for that section, all you do is use the up or down arrows there, and that changes the position of the section in relationship to the datum point. If you want a much higher fidelity in terms of the aesthetics, then you would need a lot more many points than 5 to describe the surface. 5 is just about the bare minimum you get away with. We are trying to get across to you the file. So people who are online should be able to access the aircraft file. So if you go back to the menu and use the open feature, you should be able to open the ACF file which we are referring to. So I hope that everybody now has access to the file online. Everyone done?
Yeah.
Okay, so let's go back to the standard and go back to the fuselage. The things that you need to set are the number of sections. So it's 14 in my case, and I'm using 5 points to define the curve. If you want more, then by changing the number of stations, I will get an extra section to input. Once you have decided on the number of sections, of course, we need to know where these sections are located. So the first input box tells you how far away that section is located from the datum point. One of the key things about X-Plane is if you hover the mouse pointer on any part of the screen which requires a user input, it will give you a help screen. It will tell you exactly what that input needs to be. So once all those sections are defined, then you can look at the top side and the bottom views in the wireframe mesh, which incidentally can be manipulated by dragging any of the points to create the shape you wish. Exiting the fuselage section will show you the results of your manipulation. In this case, I have just created a humpback whale. Created a couple of humps. So it's very easy to change the basic shape. The next thing you'd like to address would be the wings. So if I click on the wings, you will see that the top of the screen, you will have wing number 1. So if you were designing a biplane, you'll have 2 wings. If it's a monoplane, of course, you just have 1 wing. The second wing is blank. You will also have on the same tab the horizontal stabilizer. So clicking that, I'm able to create the horizontal stabilizer. The tab next to it is the vertical stabilizer. And you can notice that as I scroll through the menus or the tab, the section of the plane that you're working on is highlighted. So for example, if I click on wing number 1, on the right hand side, you'll see the wing is highlighted. It means that that is the active element that you're working on. So what are the sort of things that we need to set for these wings? The semi-length, which is from root to tip at 44 points. We need to set the tip chord, the root chord. Now going back to the initial calculations, I've determined the root and tip chord to be just over 1 meter long. I think they were about 1.2 meters or something. So in feet, they turn out to be 4 foot or thereabouts. So I set the root chord, I set the tip chord. We didn't have any sweep, so the sweep angle is 0. We didn't have any dihedral, so the dihedral angle is 0. But we need to locate the wing. We need to locate the wing in terms of its position from the datum. So the way X-plane works, it works on a longitudinal arm and a lateral arm, which is basically the distance away from the datum point, either in the lateral axis or the longitudinal axis. And of course, you also have the vertical axis, so you have a vertical arm as well. So the leading edge of the wing is now being located at 5.15 feet away from the datum point, which is the nose of the aircraft. The vertical arm, so we are 1 foot above the longitudinal axis. And by changing any of these numbers, you will see we change the wing position. Okay. So let's get back to where it was. Similarly, you can change the vertical position by changing where the wing sits. Now that we've defined the basic geometry of the wing, that wing is going to have a control surface known as the ailerons. So what I need to do is, firstly, select how many segments I'm going to split my semi-span. So I've chosen to split it up into 8 segments. So when I click or change that number here, so that's 1, 2, 3, 4, 5, 6, 7, and 8. So you can just carry on going until I think about 10 segments you can create. And this is where the limitation is. Because we can only create 10 segments, so the semi-span can only go in increments of 10%. So the aileron size will be in that increment. So one of the things that you notice is the first entry point is the incidence. So if I want to create a twisted wing, then each segment of that wing can have an incidence. Okay? So if you don't want to twist, that needs to be 0. Or if you want to put the wing at a particular setting angle, the entire wing, then I can set the wing at that initial angle. So I'm deciding to use 4 degrees as my wing setting angle. All right. So once I have decided on the number of segments, I then choose what is the incidence at each of those segments along the wing. The control surface that will normally be found on the wing is an aileron or flaps or anything else, and I can choose where on that semi-span that control surface lives. So by clicking aileron 1 and choosing the last 3 columns, I will make the aileron sit.
That's just late. Yeah.
So the last 3 segments of the semi-span of the wing would now be my aileron. Okay. So this is a simple aircraft. We don't want any more control surfaces. So that'd be enough for now. If we then go to the horizontal stabilizer, it's treated just like another wing. No difference. So again, we need the semi-span, which is the root to the tip at quarter chord point. We need the root chord, we need the tip chord, we need the sweep angle, we need the dihedral, we need the longitudinal arm. So longitudinal arm is effectively where the tail is sitting. And in this particular case, again, I have chosen to split my elevator or my horizontal tail into 10 segments, and I'm going to use a full length elevator. So to choose a full length elevator, all the necessary tick boxes on those columns need to be ticked. I am not going to set the horizontal tail at an incidence. So the first entry, which is the incidence, is all set to 0. So that is all set to 0. We have exactly the same procedure for the vertical stabilizer. Again, this just tends to be another surface, but vertical. So here you will see the dihedral angle. The dihedral angle here is 90 degrees. Now that puts the aerodynamic surface vertical. By changing this angle, you can see if I change it back to 0 or close to 0, you'll see the fin has become flat. So changing that back to 90, the fin is vertical again. So the dihedral angle there is to rotate the aerodynamic surface 90 degrees. Okay, so don't confuse the dihedral angle with the typical sense. This is literally a rotation of the surface 90 degrees, so it becomes vertical. If you had a detail, then obviously you could use the vertical stabilizer 2 to create the detail. If you had more than one wing, you can use wing number 2 if you are interested in producing a biplane. So that basically completes the aerodynamic setup. So we define the fuselage, we define the wing, we define the empennage. Now comes the control surfaces in terms of sizing. So we've explained that I'm using a full-length elevator. I've explained that I'm using the last 3 segments of my semi-span as ailerons. I'm using a full-length rudder in my case, but I haven't defined the sizes. So to define the sizes, I exit this menu, go to Standard, and look at Control Geometry. So we exit that menu and enter Control Geometry. Here you will see aileron number 1. The first column refers to the deflection, the chord. So we're using 20%. And then the deflection in terms of degrees up and down. So we're putting the limits on its deflection. Elevator 1, we're choosing to be 0.3 or 30% of the chord of the horizontal. And we are setting that to plus minus 40 degrees. You can set it to whatever you wish. Same goes for rudder. So these numbers would match up with the computation that we did earlier in terms of the rough percentages that we had in our design. So we've now defined the fuselage, we've defined the aerodynamic surfaces, we've defined the control surfaces. We now need to define the undercarriage. So exiting this menu allows us to go into the landing gear. And when I go into the landing gear menu, I can define what landing gear type I have by clicking on the choice. You can have skids, you can have a single wheel, you can have trucks, etc. So in our case, we'll be choosing single. Because it's tricycle, I will need to define 3 sets, the nose and the 2 just behind the CG. And that's easily done. So every time I invoke a selection, a column will appear, and in that column, I'm able to change my longitudinal arm, the vertical arm, the lateral arm, and define what kind of gear it is. So if I go back to none, the column disappears. So fuselage defined, wings defined, control surfaces defined, undercarriage defined. Now we come to the propulsion system. So going back to standard, going to engine specs. I'm going to choose an IC engine. So with the engine choices, what you'll see is I can define, if you go to engine 2, which is the second option, whether it is electric, carbureted, injected, a turbine, a turboprop, etc. So my choice is carbureted reciprocating engine. Depending on where the engine is, I can now choose to place it on the aircraft in terms of its longitudinal, lateral, and vertical arms. So that positions the engine onto my airframe. In my case, I've chosen the engine to be a foot below the axis. And the lateral and the longitudinal lateral arms are 0, so it's on the center line. Similarly, I can define the props. But the most important thing is the power for the engine. Now, I have chosen a power loading for the aircraft, and 105 horsepower is something that would fit the bill. So I set the power that the engine is going to produce. So 105 horsepower, so that is where you set it in the prop engine specs. Anything that's not used in terms of, if you've chosen a carbureted engine, then anything to do with jet engine specs, etc., you can just ignore. So you only need to put in the things that are relevant to your propulsion system. Needless to say, you can choose electric. So if you go to engine 2, you can change that to electric, but then in the systems, you will then specify how many batteries you have, which buses they're connected to, etc., etc. So again, there's a whole a raft of things that you can set on the electrical propulsion. But to keep things simple, we will leave to the, or we'll stay with the carbureted engine. So now we've got the fuselage done, the wings done, the control surface is done, the undercarriage done, the propulsion system done. But the system still doesn't know what aerodynamic surfaces we are dealing with. So the next thing to do is to go to the expert system and select the airfoils. Because the wings have now been created, I can choose the airfoils. For the propellers, we are using the Clark wire, and for the wings that we've created, we'll be using the 2410. To change the airfoil, you double-click on the box to the left. Again, you can define the airfoil for low Reynolds numbers and high Reynolds numbers. So all of those need to be defined. In my case, I've only got one airfoil, so it is fixed at a particular Reynolds number for sake of convenience and ease. So I will be using the same airfoil everywhere. So all we do is double-click, go to the airfoil section in X-plane, and select the airfoil. So in our case, it's the NACA 2410 airfoil. So double-clicking that selects the airfoil. So that's a fairly straightforward selection process. For the empennage, we have chosen a symmetrical NACA 0006. It's a thin airfoil. You could have chosen 9, you could have chosen 11, but 6 it is for me. Nice and light. So we've done now the fuselage, the wings, the control surfaces, the undercarriage, the wings. What else is left? We've done the panel. We need to now look at the weight and balance. That's the important thing. We're not going to be bothering with nacelles, and we're not going to be bothering with the nice things in life as yet. Let's concentrate on the basics. So we know where the wing is located. the leading edge. We know what the quarter point or quarter chord point is on the wing. The CG needs to be ahead of the center of pressure for it to work. So with the wing located around 6 feet leading edge, the center of pressure is going to be around 7 feet from the datum. So the CG needs to be around 6 feet at the leading edge of the wing. The range that I'm going to allow the CG to move, I can choose my limit, fore and aft. So those two columns, that's the fore, that's the aft limit, and that's the nominal CG location. At this stage, you can also specify the empty weight of the aircraft and also any payload or fuel that you may need to carry. You can specify the amount that you're carrying there as well. So weight and balance is being set. So once all of this is set, then you can give it a whirl and see whether it flies or not. So we'll leave the plane maker by saving all the changes. So once the changes have been saved, I can quit X-plane. It'll remind you again if you haven't saved. I don't want to save. Then I need to invoke X-plane and select the aircraft that I've created. Fire up X-plane. Go to new flight. And in experimental, I have my aircraft. I will choose to start off in the air, so I do a 3 nautical mile approach. Just have a quick check on the weight and balance. It is on the default position with a all-up weight of 1,800 pounds. When I'm happy, I do the start flight. Hopefully, it will position me up in the air 3 nautical miles from the runway. And hopefully the engines would already be running.
Sorry, I'm getting a call.
So let it develop a little bit of speed. Go. Start again. But this time I'm with the let. It builds up speed a little. It flies quite well. It goes to prove that even in a few hours, you can actually design something fairly stable. So has everyone got the aircraft flying? So you'll need to position yourself in the air. Change location.
Doesn't have a CD.
I will see you then.
It's on about. That's also control of it.
Right? Are you okay?
Yeah.
Fine? You fine?
Alex, which is the game about just you can you may have the explain. This is the explain that nobody's so how do you if you have like 10, 11,
There are tools, but they're not very stable. So if you look at importing CAD geometry, SITL files into explain.
You're saying this
Okay, so how are we doing? Is everybody got the aircraft flying?
Yeah. So you need to check in the experiment, there's a box for experiment control. If you accidentally put the experimental section of the box, they won't be able to see it.
Yeah, I met the it's long time ago, by the way, 2018, Olympic Society. So we won the lightweight competition. And then you came and done and then you told us about this, and we were trying to simulate our model because we won.
And that's, I can't remember.
Yeah.
So many people coming down. It's impossible. You've got the aircraft?
Yes, so you can see that as well.
Yes, you can. Sure.
I can show them the.
Right, guys, so if you want to get access to data from the flight, then what you need to do is you need to click the settings button on the right-hand side of the screen. Clicking the settings button will open up another window with lots of menu items. And the one that we are interested in from a data collection point of view is the data output window. And what you'll see are 4 columns. The first column says show in cockpit. The second column says data graph window, which means that a real-time graph of information that you wish would be displayed on the screen. Then you have the third column, which says the output to the disk. So all the data is stored in a CSV file on the computer. And finally, if you want to do software in the loop or hardware in the loop simulations, then you need to be able to send that data via a UDP packet to another computer on the network, or any device that is able to work with UDP information. To select which output you want, if you're not sure of the variable, for example, you can search for the entity by typing, for example, if I want elevator deflection, so I just type in ELEV, and item number 74 is elevator deflections. If I want to show that entity on the screen, I will click that appropriate button. And if I want that to be outputted to the data file, then I need to put that to the disk file by selecting the third column. If I want, for example, angular rates, or if I want lift coefficient, for example, item number or index number 68 is lift over drag coefficients, so that information is available too. But most importantly, you need some time reference, so you need some times. So if I type times, then various times like Zulu time, Hobbs time, real time, all that information will be outputted to the screen. So exiting that window, you will see on the left-hand side of the screen a lot of information appearing. That's where all the data is. And when I resume my flight, then that data is now going to be stored in the disk file. When I'm done with my flight and I want to access the data, then I quit Explain, and I will have a file in the Explain directory called data. Double-clicking the data file will reveal the data that you have been capturing. What Explain does, every time a change occurs, it will put out a new header, and the header contains all the variables that you have been outputting. Scrolling at the bottom allows you to see the entire file. When a change is made, for example, towards the end, we started making a change on CL and CD values, a header will appear appropriately to indicate which these values or which these columns are. This file can be taken into Excel fairly straightforwardly by opening up Excel and reading it as a delimited file, as a CSV, not as a delimited file, which allows you then to manipulate the data in Excel from a graphical point of view. Okay, any questions so far? Now you all have a file. You can play with it to your heart's content. It does fly, but if you can make it fly even better, so much the better. So for example, the things that you may want to experiment with is taper the wings, taper the fin, taper the horizontal tail, give the main wing some dihedral, okay? Play with the center of gravity, play with the taper ratio of the main wing. So those things will allow you to see how those changes affect the stability of the aircraft and the performance. If you really want to get good performance out of it, reduce the fuselage diameter. I've chosen a very large fuselage diameter, so the drag is quite high. Increase the engine power. So by manipulating those variables, you should be able to change the performance of the aircraft quite drastically. Okay. And if you then spend a lot more time in terms of skinning it, in terms of texturing it, in terms of defining the cross sections in a little bit more detail, you should be able to define and create a fairly good-looking airplane as well. So it all is a function of how much effort you put into the design. Okay. So I think I'm going to call it a day. It's almost 8:30. Thank you very much for being with us. Particular thanks to all the participants online. Thank you very much for joining. I hope you've had a good evening and a fruitful one in terms of educational value. If you have any questions, keep posting them onto the chat line, and when I do get a chance, I will try to answer them as quickly as possible. The recording will be made available. I'm sure Barry will work out a mechanism of making the recording available to you all, and the notes, the design notes, will also be put onto the same mechanism. So for now, thank you very much, and we look forward to seeing you on 15th of March for the final session. And in that session, we will be looking at how airfoils are created. We'll be looking at airfoil tools. We'll be also looking at X-foil, and we'll also be looking at XFLR5 for the quick assessment of the stability of the aircraft. Okay? Thank you very much indeed.